Hello, we are going to do the linear conduction experiment. This is our group members, Jelena, me. Okay.
Right.
So now we will turn on the main for the base unit. Okay, and then now we are going to we have already connected the thermocouples, and now we are going to connect the brass plate to the middle. And we're going to connect this thermocouple to number 4. And now we will turn on the water valve, and we must check and see whether if there's any leakage or not in the pipe. And now we will turn on the heater switch. We are also going to plug in the power supply. So in the beginning of the experiment, we have to wait until the temperature reaches to 24 degrees Celsius, and then we can start by increasing the power to 30 watts.
So after setting the ambient temperature to 26 degrees, we have to turn it up to 30 watts. Now we have to wait for the temperature to get stable.
Okay, after we recorded the temperature, the power for 50 watts, and we take the reading for T1 until T7, then we change the power to 50 watts. Okay? And we wait for the temperature to stabilize. After that, we take the reading for T1 until T7. Okay, after we do 30, 50 and 60, now we do for 70 watts and okay, for the last one is 90 watts. Okay, we make the power to 90.
Yes, leave it, let's leave it.
Okay. After we do for material for brass, then we will change this one to stainless steel and repeat the same procedure for stainless steel and stainless copper.
Very good day. My name is MOIRA PATERUS. I'm going to present the result and data analysis for our experiment on lab 1, that is linear conduction. Okay, this is the data for our experiment. So we have table 1, table 2, and another one is table 3. So for table 1 is the data we collected from the material we experiment, that is a brass. So we experiment with power 13 with 30, 50, 60, 70, and last one is 90 watts. So we set our ambient temperature until it stabilized to 24 degrees C. Then we start the experiment. So we collected all the data from T1 until TK, and then from the temperature in degree Celsius, we converted it to Kelvin. So for table 2, we do the same with stainless steel. We experiment with power of 30, 50, 60, 70, and 90 watts. So we did the same with the data, we converted it to Kelvin. So for table 3, the material is stainless copper. We start with power of 30 watts, and then for 50 watts, 60 watts, 70 watts, and 90 watts. For 90 watts, we have like a bit of an error here. It say on the screen of the apparatus, it say TH too hot, so we guess it is error. So after we collected all the data, we converted it to Kelvin. Okay, this is the data analysis for material brass. We plot a graph on temperature in Kelvin versus distance based on the data that we have collected. So it's so here that, for example, For 30 watts, it started really high, and then as the further it is from T1, it become lower. The temperature become lower. It's the same for all of the power we have experimented on. After that, we find out the gradient for each power. And the next one is data analysis for stainless steel. We do the same as the class before. We plot a graph based on the data that we have collected. So it's showing the same pattern as the brass. The further away it is from the T1 here, the lower the temperature gets. And the last one is data analysis for stainless copper. We did the same with the last two brass and stainless steel. We plotted the graph, and then we find the gradient for each hour given. And that's all from me. Thank you.
Hello, my name is Wong, and I'll talk about discussion 1, which is calculate the gradient of the chart. What does this gradient represent in the conduction equation? So the gradient represents the temperature curve on T versus X diagram. The heat is conducted in the direction of decreasing temperature, and the temperature gradient becomes negative when temperature decreases with increasing distance. Temperature gradient is physically quantity that specifies how quickly in which direction the temperature varies around a certain area. The temperature gradient is a dimensional quantity represented in degree per unit length. The rate of heat transmission through a medium is proportional to the negative gradient in temperature, and the area at right angles to that gradient through which the heat flows, according to the law of heat conduction, often known as Fourier law. So as you can see, uh, for the gradient of brass for power 30 volts is negative 4.04, as you can see here. For 30 volts, this is the gradient. It's going down. It indicates the longer the distance, the decrease of the temperature. So number 2, discussion 2, use the further study T1 and T7, given distance between them, the heat power and the bar area with equation 5 to calculate the thermal conductivity of the metal bar. Compare it with the typical value given in table 1 and explain the cause of any errors for the different value of the theoretical and experimental thermal conductivity. So first we are using brass. We're using the 50 watt set, which is T1 is 326.4 Kelvin, T7 is 302.7 Kelvin, length is 0.12 meter, the diameter is 0.055 meter. So the area we calculated, which is 2.376 times 10 power of -3, which is 0.0023. So using equation 5, the thermal conductivity versus the watts times the length divided by the area times the difference of the T1 and T2. So the first one is 63.93, the calculation for the thermal conductivity, but the typical value is 123 for brass. For stainless steel, it's 50 watts. We use T1 is 320 Kelvin, and T2 is 298.6 Kelvin, and the length is 0.12 meter. The diameter is same, 0.055 meter. So using the same formula, thermal conductivity equals to power times length divided by area times the difference of the temperature. We got stainless steel for 118, and the typical value is 16. Lastly, stainless copper, using the data of 60 volts, which we get 73.37 in the same formula. and the typical value is 123. So the calculated value for the thermal conductivity for brass is 82.53 comparing to the typical value of thermal conductivity is 123. So the stainless steel is calculated of the value for 70.8 compared to the typical value of 16. And the stainless copper is calculated for 73.02 comparing the actual value of 123. So it can be explained. So the first thing is the heat travel from the apparatus could be disturbed due to the attachment between the material are not stable or fully closed, causing the heat transfer might not be 100% successful. So the cause of error could be human error or even machine error. Could be explained by thermometer is not picking up the actual value. The power voltage might be not as accurate, and the environment might be one of the issue, such as aircon and other things. The experiment for different materials is conducted continuously, which means we switch from copper to stainless steel and stainless copper, which means we do not start the experiment for stainless steel and stainless copper with a radiant temperature of 24, which makes the next material we do experiment with might be a little bit with error, such as the stainless steel. So it's not exactly the right thermal conductivity for that. So the error can be explained with the unknown area are not in effect, formula 2.
A very good day. So today I am going to present on the discussion number 3 and conclusion. So for the discussion number 3, what can you observe from the gradient of the charts for each heater power setting? The gradient calculated seems to be having negative values. With the gradient of negative values, we can observe that each time the temperature is going downwards. As for the heater power setting, we can observe that with the increase of the power setting, the more value of gradient decrease from the chart. The more the heater power setting increases, the more the temperature increases from all the distance. This may apply to all material that has been experimented. Add a best fit line through all the results to find the overall thermal gradient. From the overall results, find the thermal resistance R value for the whole bar, and then use the thermal resistance in series method to find the R, and then the value K for the middle section. So this is the graph of temperature against distance from T1. So for the calculation, we have to find the resistance of brass, the total resistance and the mid resistance, and also we have to find the mid for K, which is a value of 14.36 watt per meter Kelvin. So for the conclusion, there are 5 points. The first is thermal paste has a silver grey substance that helps in efficient heat transfer from the middle section to the solid brass bar of uniform circular section. Second conclusion, copper has better heat transfer compared to stainless steel and brass. Third, the better the material of heat conductor, the faster will be the heat transfer. Number 4, with the formula applied, we have found that the next temperature is inversely proportional with the distance along the rod. So the further away the distance from the rod, the temperature will decrease. And the last conclusion, the fifth, some material are better heat conductors than the others. This experiment uses copper as a heat conductor, which has good thermal conductivity with the value of 125 watts per meter Kelvin. That is all from me. Thank you.